All right, guys. So what we're going to be looking at today, okay, I think a lot of the concepts or ideas are going to be fairly familiar to you, okay, but kind of the context we put them in might be new. Right? And what I mean by that is we're going to be looking at things like heat transfer. Okay? That would be things like conduction, convection, and radiation, which you would have learned about in junior high science. Okay? But we're going to look at them kind of on a larger scale. I'm going to talk about the water cycle again. You've only been beaten over the head with that about 10 times, okay, throughout your school career. So we're going to look at that again, but this time we're looking at it from an energy perspective rather than, I mean, you still need to know the parts of the water cycle, but in this time it's going to be about where does the energy go in, where does the energy come out of the water cycle. Okay, so it's a little bit different. Okay, and we're going to look at all the parts of the Earth and how they interact to help transfer energy from one part of the world to another. Okay, and that's kind of the big theme in this unit is energy transfers on a global scale. Okay, so we got to understand the three parts of the Earth. Okay, when we're splitting the Earth up into three parts, those three parts would be the atmosphere, which is all the gas. Okay, the hydrosphere, that's all the water. Okay, and the lithosphere, that's all the rock and stone and other parts, solid parts of the Earth. Okay, we got to look at how energy on Earth is absorbed, used, and reflected. That is probably going to be the biggest part of this lesson. Okay, how energy on Earth is absorbed, used, and reflected, because those are the three fates of solar energy. Okay, basically all the energy that drives everything on Earth comes to us from that big bright orange thing in the sky. Okay, now when the light reaches us from the sun, three things can happen to it. Okay? Some of it can be absorbed. Okay? If that happens, then the temperature and energy of that area will go up. Okay? If you absorb energy, temperature goes up, okay? Energy goes up in general. It can be reflected. If it's reflected, that means it just bounces off. Okay? Nothing is absorbed, so there's no change in energy. It simply reflects away. Right? And the third fate is that some of it can be used. Okay? And another word for used is converted. There is only one natural process that can take solar energy and convert it into another form. What process is that? Photosynthesis. Okay, so the third thing that can happen is that energy strikes something photosynthetic. Okay, and when that happens, it is converted from light to chemical energy in the form of sugar. Okay. All right, so the three fates is something that's going to come up over and over and over again, okay, in this lesson. Okay, three things can happen to energy, and we're going to talk about what determines how much is absorbed, how much is reflected, okay, how much is converted or used by plants in photosynthesis. Okay, and that lastly, the energy that the Earth receives and the Earth itself and all of its systems interact to produce the conditions necessary to support life. All right, so the first thing that light encounters when it reaches the Earth is our atmosphere. Okay? That's probably a good thing because our atmosphere is like a big shield. Okay? And it protects us from some of the really nasty stuff that the sun spits out every day. Okay? Surrounding the Earth, okay, is this magnetic shield called our magnetic field, our magnetosphere. Okay, that is caused by us having basically a spinning semi-liquid core of iron, okay, in the center of the Earth, okay, that is basically a giant electromagnet, okay, and produces a huge magnetic field around the planet, okay, that basically deflects incoming solar radiation, especially when it is most intense and may contain lots of high energy particles. Okay, when that happens, what do we see? If the sun is particularly active.
The northern lights.
That's when we see the northern lights. Yeah, I mean, if you live up north, you see them a lot more often. Okay, but for us to see them this far south, all right? There has to be a much greater intensity of solar prominences and mass ejections and things like that going on, so that those particles then smash into our magnetic field, and when they slow down, they give off visible light, okay? And we see that as the aurora borealis, okay? Basically, that is us being able to see the magnetic field, keeping us safe, okay? Can it always completely protect us? No, okay? There have been incidences in the past where a magnetic storm from the sun is simply too much for the magnetic field to deflect, and it can interfere with our power grid. Okay? Those high energy particles get through, and when they encounter current carrying wires, they induce a current in them, sometimes massive. Okay? So much so that it usually blows up power stations and causes massive power outages that cannot be quickly fixed. Okay? So it is something that is concerning, okay, for a society that depends very much on electricity and electricity transferred through wires. Okay? So it is something that we have to be concerned with for sure, especially given the same thing could happen to any electronic device that could be struck by those high energy particles. It's basically the same as having an EMP, okay? An electromagnetic pulse weapon, same thing happens. Okay? So that stuff is all very high. Okay, very far above the Earth's surface. Okay, we're not concerned too much in terms of the role they play in energy transfer for things like the exosphere or the thermosphere or the mesosphere, or even really the stratosphere, because they're so far up and the air is so thin in those parts that they really don't play much of a role. Okay, we're most concerned with the troposphere. That's the part of the atmosphere that weather generally occurs in. Some really tall cumulonimbus clouds might end up in the stratosphere. The jet stream is kind of up there as well. Okay? So, the troposphere is the part of the Earth's atmosphere that can sustain life, basically. Okay? Is it possible to stand on a point on the Earth's surface that is higher than the top of the troposphere? It is. There are several points on the Earth's surface that go up into the stratosphere. Okay, those would be the highest peaks in the world. Okay, Everest, K2, okay, places like that. What do they call the area near the top of those?
Dangerous.
Yeah, it is dangerous, but it has a nickname that sounds dangerous. You guys haven't watched very many mountaineering videos, have you? It is called the death zone. Okay, once you get above a certain altitude, okay, the air is so thin that your body cannot sustain itself long term. And by long term, I mean more than a few days. Okay, there is not enough atmospheric pressure to keep the fluids that are the gases and things like that that are normally in your blood. They start to try and come out, and they usually end up collecting as fluid in the lungs, okay, giving you sometimes what's called the Kumbu cough. Okay, but is mostly pulmonary edema, okay, which is, yeah, not good, and it's what killed a lot of climbers. So you can't sustain life above that altitude because it's just not, the air's not thick enough. It's also ridiculously cold, okay, and things like that. So it's not a place where you want to end up. Okay, like if you ever get a chance, you'll fall down the rabbit hole if you start. But okay, watch some videos on Everest, and the markers they use along the trail to the summit are people. Yeah, like there's green boots, and there's all these different bodies that are somewhat exposed, and that's how you tell where you are on your ascent to the top.
Isn't there that Sherpa dude who walked fully up Everest in like 10 hours?
Yeah, there's one Sherpa, he holds the
He can
ascent
spend a
record.
bunch of hours at the top.
You can spend
without
hours,
oxygen.
yes, without oxygen.
Yeah.
But a person like that lives at that very high altitude, and he's probably an impressive physical specimen.
Yeah.
But yeah, it's not something that most humans can do, and most humans do not ascend Everest without oxygen. That's generally considered to be not a good idea. Okay. Most people die when they run out of oxygen.
I think I got it.
Yeah. Okay. So the troposphere is the thickest part of the atmosphere. It's where wind and weather and stuff like that generally occurs. Okay, we said some of that stuff can end up in the stratosphere, but okay, we're talking about maybe the jet stream and a few really tall cumulonimbus clouds and stuff like that might end up there. All right, those are the two parts that we would be most concerned with. Am I ever going to ask you to label that diagram?
Maybe.
Never. Okay, never going to ask you about the names of the layers of the atmosphere. Okay, just outlining that we're only concerned with like the lowest 11 kilometers or All right, so the atmosphere and climate. So when the sun's energy strikes the Earth's atmosphere, some of it gets reflected by clouds, because clouds are what color?
White.
White. Okay? White is the most reflective color. Okay? It is why if you have two identical cars sitting next to each other in a parking lot, and the only difference is one is white and one is black. Okay? The black car will be hot to the touch on a sunny day, and the white car won't. Okay? Because white reflects most of the energy away, and black absorbs all of the energy. Okay? So wearing something that's very dark in color on a hot sunny day is going to make you feel hotter than wearing something light in color. Okay? Because light colors reflect more than dark colors do. Make sense? Okay, so the tops of clouds are very, very white, and they reflect away some of the incoming radiation. Okay? A lot of the incoming radiation is backscattered. That means it comes in and it hits particles in the atmosphere and changes direction, and it gets scattered randomly all over the place. What does that cause? It causes the sky to be blue. That is why the sky is blue. Someone along the way probably told you it's because the ocean, the light reflects off the ocean, and the ocean is blue.
So many fourth graders lied to
The sky
me.
be green if you stand on it.
Well, actually, the sky should be transparent because the ocean is clear, water is clear. The only reason the ocean appears blue is because it reflects the sky. That's why. Because the ocean isn't always blue. If it's a cloudy day, the ocean's a different color. It's whatever color the sky is. Okay? But the sky, okay, is actually blue because of backscattering. It's also why when we have those really smoky days, the sky isn't blue. Okay? Because when we have those smoky days, the composition of the atmosphere is different. There's a lot of ash and particulate. They scatter different wavelengths of light than the normal atmosphere does. Okay? A normal clear day, blue is backscattered. On a smoky day, orange and red are. It's why sunsets are also orange and red. When the sun is close to the horizon, it is going through the part of the atmosphere that contains more dust, ash, smoke, things like that. Okay? That's why sunsets and sunrises, the sky is orange. Okay? But as the day progresses, it gets blue. Okay? So it makes sense? Now you know for sure, for real, why the sky is blue.
I mean, I had a lot of fourth graders tell me different stuff. Am I going to have another teacher tell me something different?
You will not. I'm telling you the truth. I also tell you the earth is round.
It's flat, I'm telling you.
Yeah.
Look at that diagram right
It's
there.
actually.
Yeah. Looks pretty flat to me on
But
the
that's only a
right.
piece of it.
No, it
It's just a
looks pretty
small enough
flat.
piece you can't see the
No,
curve.
but see how it looks flat and not circular?
I'm telling you it's flat.
Okay, so you got the backscattering of the radiation. Okay, so some of the radiation goes kind of back, and it doesn't really influence temperature very much. Okay, now some of the solar radiation is actually absorbed by the atmosphere. Okay, and that can warm the air. Okay, some of it hits the surface and reflects away. Some of it is absorbed by the surface. Okay, and some of that reflected stuff, okay, goes out as outgoing long wave radiation. Some of it goes back as basically just visible light. Okay, this here would be part of what we would term the greenhouse effect. Okay, long wave radiation is things like infrared radiation, which is heat. Okay, and when that goes off out of the Earth's crust, okay, and hits greenhouse gases and things like that, it comes back down. The more times it goes through the Earth's atmosphere, the greater the chance of it being absorbed and warming the Earth. Okay, now is the greenhouse effect all bad? It's not. Okay, without a greenhouse effect, Earth would be a snowball. Okay, we need some greenhouse gases in the atmosphere to keep the Earth habitable and warm. Do we need as many as we have right now? No. Okay, the greenhouse effect is increasing. Okay, that is not a good thing. The Earth is going to get warmer as a result of that. Okay, but not having a greenhouse effect at all, okay, is not good either. The greenhouse effect gets a really bad rap. Okay, it is not all bad. Right? We need some greenhouse effect. Okay, we're kind of the Goldilocks of our solar system in terms of greenhouse effect. Okay, our next door neighbor Venus has way too much greenhouse effect. Okay, and as a result, it is hot enough on the surface to melt lead. It is hotter on the surface of Venus than the inside of your oven on the self-cleaning cycle. Okay, that is a runaway greenhouse effect. That is bad. We don't want to be like that. Okay, on the other side of the coin, our other neighbor Mars has basically no greenhouse effect. Okay, it has an incredibly thin atmosphere and has no ability to retain solar energy, so it's frozen. Okay, so we got to have that happy medium. Some greenhouse gases are good and important for maintaining temperature. Okay, All right, now, last thing on this slide, probably the most important thing in the first half of this lesson, and that is this term right here. Okay, albedo. You're going to need to know that. Okay, so albedo refers to the reflectivity of the Earth's surface at any given location. Okay, a high albedo means that that part of the Earth is very reflective. A low albedo means that most of the energy is being absorbed. So which color has the highest albedo? White or black?
White.
Right. White has the highest albedo because it is the most reflective color. Okay? Black absorbs everything. Okay? It's like think of this, a black hole. What comes out of a black hole? Nothing, because black absorbs everything. Okay? A black hole literally absorbs everything. Okay? Not even light can escape it. Okay? All right, so by that notion then, if I were to wear something that was completely black, would you be able to see it?
I don't know. Probably not.
Probably not. I mean, you'd see the absence of something, but you wouldn't be able to make out any details on that perfectly black
it's like those
material.
cars painted with that really black paint and it just looks like a silhouette.
Kind of, yeah. Okay? Because the only reason we see things is because they reflect back to us. Okay? So if I'm looking at Chloe's yellow shirt, I see yellow because that's reflecting yellow back to me. Okay? Whereas if I look at something that's blue, okay, it's reflecting blue light back to me. Right? Something that's black is probably reflecting a lot of dark blue. Okay, but probably not a lot of black. If it was purely black, I wouldn't be able to see any detail because it wouldn't be reflecting anything back for me to see. Okay, and that's how we've identified black holes. Okay, it's basically because of the absence of anything. Okay, it's like really weird. There seems to be this hole in the. That's why they got the name. No, there's this hole there. They don't really have. There's nothing there to see because everything is being absorbed. Okay, so here's what that means in terms of energy. If I look at the same place, let's say this is like a patch of land outside of Okotoks. Okay? In the summertime, the albedo of that area is much, much lower. Okay? Because it's dark. Okay? The dirt is exposed, the plants are green, okay? And the amount of solar radiation coming in and being absorbed versus reflected is very different. Okay? During the summer, 70% of the incoming solar radiation is going to be absorbed. Okay? And that's going to cause the area to be warmer. Okay? Some of that 70% is actually going to be converted by photosynthesis, but we still consider it absorbed because it's coming to the earth and staying there. Okay? About 10% would reflect off of water bodies, okay? Lakes and ponds and things like that, and about 20% would reflect off of light-colored materials, okay, on the Earth's surface. All right? So the bulk of the incoming radiation is being absorbed in the summer because the albedo is lower. If we look outside right now, okay, the fact that it's cold outside has to do with, the tilt of the Earth, but it's exacerbated by the fact that the ground is covered in
Snow.
what color is snow?
White.
Yeah, unless
Usually.
it's the yellow kind. But generally, we're talking about the white snow. Okay, don't eat the yellow stuff.
Why not? It's lemonade flavored.
It tastes like lemon snow cone.
Okay, don't eat the yellow snow. Now, if we're covered in white snow, that means 85 to 90% of the pathetic amount of solar radiation coming in December and January gets reflected away. So there's no chance for even that amount of solar energy coming in to actually do any good because it just bounces off the white snow.
That's why I get
Okay.
sunburned.
What's that? You can get a sunburn while you're skiing, yes, for a couple of reasons. You're at a high altitude where you're exposed to more UV. But yeah, there's reflection off of the snow. Yeah. Okay, about 10 to 15% of it's going to be absorbed, and most of that is going to be absorbed by maybe a rock that's poking out through the snow or trees that are poking out through the snow. But are trees carrying out any photosynthesis?
Some of them. Maybe.
No, not even the pine trees are going to be doing any photosynthesis because it requires water to be transported, and water can't be transported in frozen
Then what's
conditions.
the point of being green in the winter?
Well, they just don't have to make new leaves every year, or not as many.
I
They
thought
grow
it was
new
way
leaves,
more
but-
fun than that.
Think about how much
Kinda disappointing.
energy a deciduous tree uses to build an entirely new set of foliage every year. If you're an evergreen, you only have to grow a little bit of new growth on the end of every branch as opposed to replace every single leaf from the year before, right?
Still bored.
Okay, so does that make sense? Okay, so the application of this, okay, is first off on a global scale, areas covered in snow aren't going to absorb very much energy, and places that aren't or that are darker in color, okay, they're going to absorb more, right? Like if you're on, like, let's say a dark sandy beach, okay, does the sand get really hot? Okay, like some places they actually put like a soaker hose out on the beach so that you can walk on sand that's wet so you don't burn your feet. Okay, it can get that hot. So yeah, we gotta kind of watch out for that. Now here's the application that you would be asked to kind of apply this to. I might say, here's a structure or a device and tell me how it might be used to keep something cold or keep something warm. Okay, and you would have to talk about maybe it's light in color. Like maybe it's a quinsy. Has anyone ever built a quinsy? A snow shelter?
No.
Okay, where you basically make a pile of snow and then you hollow it out.
Oh.
Okay, it's called a quinsy. Okay, why does a quinsy work? Why does it keep you warm?
Snow's an insulator.
Snow is a good insulator. There's lots of tiny air pockets, which we'll talk about when we talk about convection. But also, when you crawl inside, snow's what color? What's it doing to all your radiation? It's reflecting it back to you. Okay, so all of the heat that radiates away from you, okay, that could be seen with like a FLIR camera, an infrared camera, okay, all of that hits the snow and comes back to you. It doesn't escape. Okay, snow is actually a great insulator. All right, making sense on that albedo stuff? Okay, so those are going to be kind of the applications there. Okay, so gases present in the Earth's atmosphere. We already talked a little bit about the greenhouse effect. Okay, so carbon dioxide, that's a greenhouse gas. CFCs, methane, okay, ozone, nitrous oxide, okay, they're all greenhouse gases. Even water is a greenhouse gas. Okay, so if you have water vapor, it can act as a greenhouse gas as well. All right. So basically that just allows the solar radiation to bounce around a few times, and the more times it bounces around, the greater the chance it can be absorbed, which obviously then increases the temperature. Okay. I was trying to find a good picture of what a rain shadow effect looked like, and I found this one. Okay. So this is Mount Robson, and it's in the Canadian Rockies just west of Jasper. Okay. And lots of days you cannot see the top of it. Okay? Even though the rest of the sky is clear. And that's because it's so tall. If you get a moist air pocket, okay, and it's moving towards the peak, it gets pushed up and over, and as soon as it gets to about this altitude, it gets cold enough that all the water forms a cloud. This cloud will literally form out of nowhere. Okay? It'll just be clear. I'm looking at the top of the peak, and then all of a sudden a cloud appears. Okay? Because this pocket of moisture is moving towards it, and it gets high enough that all the water vapor that was normally invisible because it was a vapor, okay, suddenly condenses, okay, and I can see this cloud, and as the cloud moves over the top and then goes down the other side, it disappears, and there's a fresh dusting of snow on the top of the mountain, and it happens several times a day. Okay? So it's a pretty interesting thing, and it's kind of how that rain shadow effect we talked about the other day works. Okay, so that's the atmosphere. Okay, talked about its role. Okay, now the hydrosphere, that is all the water on, above, under the Earth's surface, okay, is the hydrosphere. It can be water vapor, it can be liquid water, it can be ice, okay. Less than 0.1% of all the water evaporated from the surface of the Earth is returned to the area it actually comes from, okay. So the rest returns to the ocean, okay, via rivers, or falls as snow and is trapped basically in an ice cap or a glacier or something like that. Okay, so if we're looking at kind of the percentages here, okay, this would be fresh water. Okay, so this would be all the water on Earth right here. 97% of all the water on Earth is in the oceans and is salty. Okay, 3% of that water is fresh. Okay, 3% of the water on Earth is fresh. So if we're looking at that 3%, more than 2/3 of it is frozen. Okay, it's in ice caps and glaciers and things like that. Okay, about 1/3 of it, okay, or just a little less than 1/3 of it, is groundwater, and this other amount here, this tiny little amount, is the surface fresh water, lakes, swamps, rivers. okay? So we depend a great deal on a very small amount of something, okay? Which also makes Canada, in terms of water, one of the richest places in the world, okay? We have more fresh water than pretty much anywhere else, in terms of glaciers, rivers, lakes, things like that, okay?
We're just cool like that.
Yeah. Okay, so the water cycle. All right, you probably know the parts, but we're going to quickly review them. Okay, there's two ways that liquid water turns into a vapor. Evaporation, that's directly from liquid water in an ocean or a lake or a river, evaporating into water vapor. And the other way is evapotranspiration. That is water evaporated from plants as they carry out photosynthesis. Okay, both those processes are energy intensive. They require energy. That's supposed to be a cue. I did that tail wrong. Okay, so energy is required for those. Huge amounts of it, actually. Okay, to give you an idea, for 1 milliliter of water to evaporate into water vapor requires 2,260 joules of energy. Is that a lot?
Sounds like a lot.
It is a lot. It is a huge amount of energy. Because 1 milliliter is tiny. Okay? It is like a medium-sized drop of water. That's 1 milliliter. Okay? That requires 2,260 joules of energy to evaporate. So when you see a cloud traveling through the sky, in that cloud are thousands or maybe even millions of liters of water vapor. Does that cloud represent a lot of stored energy?
Yeah, like billions of joules.
Yes, billions of joules. Okay, so the water cycle is a way for energy to move from one place to another. Near the equator, where there's lots of intense sunlight, water and lots of ocean, water easily evaporates and goes into the atmosphere. And then wind moves it, okay? Blows the clouds, storms, whatever, to other places. Okay? When that stuff gets to a point where it's going to condense back into either a liquid form or if it's going to become snow or hail or whatever else, okay, that condensation releases the energy. Okay? So energy can move from, let's say, more tropical, okay, equatorial areas to more northerly or high latitude areas through water vapor, okay, or what we call latent heat. Okay? So this process here is often referred to as latent heat. That's something we're going to talk a lot about actually in this unit, okay, because it represents huge amounts of energy moving from one place to another. Okay? It's still from the sun. The sun is what causes that water to become a vapor. Okay? But that energy doesn't necessarily have to strike a particular area for it to arrive there. It can be transported there through the clouds and through the water cycle. Okay? Now, when this energy is released and the condensation and the precipitation all fall, okay, that water has gravitational potential energy as well, doesn't it? Okay? So when it falls and it hits the earth and it starts running in runoff, okay, so in rivers and streams and things like that, okay, does it also have energy? It has mechanical energy. And that mechanical energy also came from the sun. The sun is the reason it was up way high up in the atmosphere. Okay? It evaporated, okay? It gained energy, right? And as a result, we can harness that, okay, with hydroelectric dams and things like that. Okay? So there's lots of places, okay, where energy can be released in the water cycle. Okay? There is so much energy in that running water, then it can carve canyons in the rock. No, not immediately, obviously, okay, but over millions of years, okay, we can, cut into rock and make a Grand Canyon. Okay, that's kind of what happens. Making sense? Okay, so the water cycle is about energy transfer, okay? But in order for that energy to be transferred, a lot of energy is required, okay? Huge amounts of it, which is why areas like Antarctica are incredibly low energy, okay? They're covered in ice, which is white and reflective, okay? They don't receive a lot of light, and what light they receive is low angle, okay? And not much of it gets absorbed, okay? So basically their water cycle doesn't run, okay? The only reason they get any precipitation is because it blows in from somewhere else, okay? What's the driest continent on Earth? Antarctica. Okay? Even though it's covered in glaciers that are in some places over a kilometer thick, they're only there because Antarctica's been at the bottom of the world for millions of years and it's had time to build up. Okay? Over that amount of time, even small amounts of snow are going to build up into glaciers. Okay? But it gets the least amount of precipitation of any location on Earth. Okay? And that's because the water cycle just doesn't run there. Okay? There's not enough energy to get it going. All right? Making sense? All right, so you still need to know the parts of the water cycle. So you still need to know evaporation, evapotranspiration, condensation, precipitation, infiltration, that's water going into the ground, okay, and surface runoff. Okay, still need to know all of those parts. All right, so the hydrosphere, we just talked about this. Most of the water on Earth is salty, okay? Only a small portion is fresh, okay? And we see lots of different forms, including groundwater. Okay? Groundwater is exceptionally important in most places of the world, okay? In fact, we get the bulk of our drinking water not from the Sheep River, but from wells. Okay? If you live on a farm and you have your own well, okay, you are tapping an aquifer, which is basically an underground area of rock that is inundated with water. Okay. All right, and those aquifers are recharged by rainfall. So is there a danger that wells can dry up? Yeah, okay. One of the main things that recharges groundwater is wetlands. So if you've got a slough or a swamp, okay, somewhere, and the water is just sitting there, that water is slowly filtering through the earth in a process called infiltration, okay, and it's getting into these aquifers and keeping them filled up. All right. If wetlands are destroyed or they dry up naturally, okay, the wells and aquifers in that area are also going to be in danger of drying up. All right. And is this a huge storage, water storage structure?
Mm-hmm.
Yeah, glaciers, like we're very lucky. We have lots of glaciers. They're shrinking, okay, all the time, okay, but they store a lot of fresh water, and as a result, a lot of stored energy as well. As they melt and the water runs off, obviously it gets into rivers, and we talked about that mechanical energy. Okay, to give you some idea, this is the Robson Glacier. Okay, now the Robson Glacier used to be, it's quite long, but it also used to fill up the whole valley up to these points. So it's not just shrunk lengthwise, it's also shrunk depthwise. Okay? When we hiked this trail, we came across this meadow, and in this meadow was a sign, and that sign said, in 1901, the Alpine Club of Canada marked this point as the toe of the Robson Glacier. We looked at that sign, and then we looked around, and we could not see a glacier. That picture was taken in 2003. In 102 years, the glacier receded over 2 kilometers. Okay, that's not just length, that's also depth. Are they shrinking pretty fast? Okay, something we have to be concerned with, especially when we have a year like this where we get very little snow. Okay, it's the snow that keeps those glaciers going. If they get exposed, okay, and let's say it's a forest fire season and a bunch of ash falls onto those glaciers and dust falls onto those glaciers and they don't get a fresh covering of snow, what happens to their albedo? It decreases, right? Because they'll be darker in color, right? And they'll melt faster. Okay. In addition to that, as they melt, more dark rock around them is exposed. That dark rock has a lower albedo, it absorbs more solar energy. The process of that melting is accelerated by basically everything. okay? So there's big concerns about that. It's actually also one of the reasons why we put sand out on the ice on the roads when it gets icy and snowy. And part of it is for traction, but the other part of it is it's dark in color, okay? And it helps the snow to melt faster when the sun gets on, okay? And we also throw salt in it, which lowers the melting point of the ice, okay? There's lots of logic to why we do those things, okay? Yes, sand immediately helps with traction, but it also lowers the albedo of the snow, making it melt more quickly. All right, then we got the lithosphere, okay? So the lithosphere is all the rock on Earth, no matter how small, okay? To a geologist, there is no such thing as sand. Every grain of sand is an individual rock, okay? Because it's true, sand comes from the weathering of rock. So you just have, when you have a whole bunch of sand in an area, you just have a bunch of little bits of weathered rock. All right, so the most important part of the lithosphere in terms of living organisms is the topmost layer, and that is the soil. Okay, how many of you ever dug a hole? Hey, what'd you notice when you got, a few feet down? Okay, there's clay underneath. Keep going, what do you hit? Oh, okay, because in Okotoks, you don't have to dig very far before you hit this.
Bedrock.
Bedrock. Okay, I know this from experience. I've had to build decks and fences in a few houses in this town, and I have hit bedrock as low as this much. Okay, had a bobcat come in and he started digging. He's like, I can't go any lower. I'm like, what? Well, we'll just dig out that rock. He's like, no, you don't. That's the bedrock right there. It's sandstone. It's not going anywhere. Okay, and then when they dug the hole for our house up in Westmount, okay, they had to bring in a special device they put on the arm of the backhoe, basically a jackhammer, because they hit the bedrock and they had to jackhammer it to break it into pieces. They pulled one piece out of there the size of a Honda Civic. Okay, that was just the pieces it broke into, and that bedrock was only down a few feet. Okay, that doesn't take long in certain parts of this town for you to hit the bedrock. There's a huge outcropping of sandstone right around here, okay, and it's very, very shallow. Okay, but there are layers to the soil. Okay, so soil is the topmost layer of the Earth's surface. It's obviously the layer in which plants grow. It is its own ecosystem. Okay, it has biotic and abiotic components like we talked about in Unit 2. Okay, there's non-living things. That would be, the minerals and the rocks and the, things like that. And there'd be also the living things, the bugs and the bacteria and all the other stuff that lives in the dirt. Now, is all soil created equal?
No.
Definitely not. That's soil. Would you want to plant your garden in that?
No.
But you could, but you wouldn't have a lot of work to do because nothing's going to grow there, okay? Just this mesquite bush that can, basically grow anywhere.
Does the garden there also involve you putting a house there? Because that would be a cool place to live.
Maybe, if you could get any drinking water.
Just put a tube down to the river.
That's not a
When the
river.
snow comes and you die.
That's a dried up lake bed.
Just fill it back up.
Oh, we'll just fill, okay, it's like a bathtub.
Just find a glacier and place it there. Cover it with black stuff.
Right.
Grab a hose.
Yeah, just do like your neighbor's hose or
Yeah,
something.
just like filling the kiddie pool.
So that they have to pay for it.
You're devious. Okay, yeah, so not all soil is created equal, but it all comes from the same place. Soil is a combination of decaying organisms and broken down rock, eroded rock. Okay, younger soils tend to be thinner. Okay, they're going to have less of that organic decaying material and larger chunks of the broken down rock. So if you kind of go up into the mountains, okay, soil tends to get thinner and thinner and thinner and more rocky as you go up because that soil is younger. Okay, it has more recently been exposed from underneath the glacier. Okay, because if you go back, a few tens of thousands of years, okay, if you were standing right here, you'd be under a kilometer thick sheet of ice. Okay? The Laurentide ice sheet would have covered this entire area. Right? So the younger a soil is, the bigger the chunks of rock and the thinner it will be. Okay? Okay, so when you dig a hole, this is what you see. Okay, you see topsoil. Okay, usually darker in color. Okay, but it's different from place to place. Okay, topsoil here tends to be a bit sandy, so it's gritty between your fingers. Okay, and that's because it comes from the erosion of our bedrock, which is sandstone. Okay, if you go further north, okay, to an area where the bedrock is limestone, the soil is darker, and if you put it between your fingers and rub it together, okay, it feels more like baking soda. Okay, because limestone erodes into a very fine material as opposed to sandstone, which erodes into sand, which is very gritty. Okay, and that gives soil different qualities. Okay, soil with very fine particles tends to retain moisture very well. Soil with larger particles tends to dry out faster. Okay, so in all soils, you will have, we don't worry about that part. Okay, we have the topsoil, which is obviously on the top, hence the name. Okay, that is where you're going to find, most of the plant growth going on, most of the bacteria and bugs and worms and things like that. Okay, that's where the bulk of the living activity is going to go on. Okay, below that, you're going to have what's called the subsoil, and the subsoil is clay. Okay, and that's the same anywhere you go. In fact, if you had a sandbox as a kid, you might have noticed that if you dug down through the sand, there was clay underneath. Anybody ever notice that? Okay? Kind of depends how big your sandbox was, but. Okay. Your parents didn't put clay in there. Clay collects in there. Okay? And here's why. Sand has big particles. Okay? So these big particles, they can't fit together tightly. So there's spaces in between them. Clay particles are tiny. They're basically dust that settles on your sandbox. Okay? When it rains, those fine particles get washed down in the gaps between the larger particles. And so clay always collects underneath the topsoil because it's smaller. Right? Does that sort of make sense? Okay? Now, clay holds onto moisture very, very well. Okay? So that layer is almost always wet, okay? Or at least moist. Okay? Underneath that layer, you're going to find weathered or decomposed rock or solid rock. Okay? Both of those are called the parent material, because they are where B and A come from. Okay? They're the parent material for that. So the horizons we deal with are the A horizon, the B horizon, and the C horizon. Okay? The A horizon is the topsoil, the B horizon is the clay, okay? And the C horizon is the parent material or bedrock. Okay, the A horizon, like we said, is the topsoil. Okay, mixture of rock, living organisms, decaying organic matter, that's dead plants and animals. Okay, usually darker in color. Okay, and you have, so this would be A, this would be B, that would be C down below. Okay, the picture on the right is a typical soil profile for a prairie. Okay, prairies typically have very thick topsoil. Okay? And the reason they have that is every year the blades of grass, or the grasses from the year before, are going to be decomposed, and a new grass will grow up through it. Okay, so there's always this layer of thatch, okay, that is going to be decomposed and turned into topsoil over time. The same would be true in a deciduous forest, where every year the leaves are shed. Those leaves become a layer of decomposing material. They typically also have fairly thick A horizons. Okay, B horizon is quite a bit thinner, okay, and then you got the C horizon quite a bit further down. All right, so B horizon, little or no organic matter, okay, rock is less decomposed, and there's lots of clay. Okay, this here and this here are pictures of the soil profile for a tropical rainforest. What do you notice is thin to absent?
The sea horizon.
Well, C horizon is going to be here. It's going to be a little thinner than the B horizon for sure, but it's the topsoil.
Is that because they get so much rain?
It is. The topsoil washes away all the time. Okay? Now, it's weird. It's counterintuitive to think that a jungle could grow in a place where the dirt is so bad. Okay? But tropical rainforests have some of the most nutrient-poor soil anywhere. And that's because they're flooded most of the time. The topsoil just washes away. The plants pull their nutrients out of the floodwater, okay, which is full of nutrients because it's eroding the soil and carrying it everywhere. Okay? You don't want to try and farm in an area that was a tropical rainforest. For one, it'll get flooded all the time. Okay? And secondly, the soil is going to be really, really poor. Okay? So very little A horizon and mostly clay, because clay kind of cements itself together and doesn't really wash away. All right, and then you got the C horizon. Okay, this is a soil profile, I think, from just outside of Okotoks. Okay, so this here would be our A horizon to about here. Okay, the B horizon would be kind of along here. There are chunks of rock all the way up. Okay, that's just the way it works, right? But then the bulk of the sandstone, okay, broken up, obviously, is the C horizon. Okay, so it's a pretty typical soil profile. Okay. Making sense? All right, you know what? I'm going to give you guys about a 5-minute break here, and then we'll keep going on the energy stuff here. Okay, so now we're going to talk about energy transfers, okay, things like that on a global scale. Obviously, the Earth is a system, and it is not this simple. Okay? It is not a matter of energy comes in and it either bounces off or gets absorbed. Okay? It is far more complex than that.
That picture's wrong.
No, it isn't.
Yeah,
Because
it
the
is.
Earth's round.
No, it's flat, I'm telling you.
It looks
It's
flat. Like it's
actually
it's
triangular.
a
Think of it like a dinner plate, and there's like a giant man underneath who has big wings, and he's holding up the plate
Oh
to the sun.
God. You should,
Yeah,
you
that's
should
gone.
encourage that. 'Cause it's
Every day, it gets more crazy. Okay.
Don't piss him off.
All right. So, the sun, as we said, is the most important and most dominant input of energy to the Earth. Okay? Are there other forms of energy on Earth? Yes, but they're so small by comparison as to be essentially negligible. Okay? That includes geothermal. Okay? I know when we see like a volcano erupt, it's usually a humanitarian disaster. It's there's lava or ash and all kinds of stuff that is obviously very destructive. But you have to remember that those only happen periodically. Okay? They do kind of show us what's going on beneath the Earth's surface, but it's a bit more difficult for us to access that. Okay? There are some places on Earth that do use geothermal energy as a form of heating their homes and things like that. Okay? But you sort of have to be in the right place for that to work. Like, we couldn't really use that here in the middle of a stable continental body. Okay? But if you lived in like Iceland, yeah, absolutely, geothermal is totally an option there. Okay? The downside of geothermal is you usually have to be near something geologically active. Okay? So there's that whole, do I want to have a volcano next to me kind of thing. Okay? All right, so the biggest thing is input from the sun. We're not going to worry about those other forms of energy that are present simply because they're so small. Okay, so there are 3 ways that heat can be transferred. Okay? Those methods are conduction, convection, and radiation. Okay? Conduction, convection, and radiation. Now, conduction happens in solid objects only. Okay? So, conduction is heat transfer by particle motion. So, anyone ever been in a mosh pit?
Yes.
Okay? So, conduction is like a mosh pit. Okay? If you can imagine all the little particles, okay, that would make up, let's say, an iron bar. Okay? They're all packed in there, really, really tight. So tightly that they can't move past each other. Okay? That's why a solid cannot take the shape of its container, but a liquid can. Okay? In a liquid, the particles are further apart. They can move around, they can switch places, so a fluid, like water, can flow, okay, and take the shape of its container. I can't pour an iron bar. Okay? It just is not gonna take the shape of its container because the particles are really, really close together, right? Now, if I heat up one end of the iron bar, so if I do kind of what it shows here, okay, and I put one end of the iron bar in a flame, okay, what's eventually going to happen? Eventually, I'm not very long after, okay, I'm probably going to burn my hand. Iron is a pretty good conductor of heat. Okay? Now what happens is the particles in the iron bar that are over here exposed to the flame gain energy and they start to move faster. And when they move faster, they run into each other and they transfer that energy to other particles and they get moving faster. And eventually they hit other particles. Okay? And it's almost like a domino effect that transfers energy along the solid object simply by having particles run into each other. Okay? That's conduction. The energy is conducted from one end of the solid object to the other by simply having particles run into each other and run into each other and run into each other, almost like a fire brigade, like a bucket brigade, okay? Transferring the water buckets from one end to the other. Okay? Transferring that energy along by running into each other. Making sense? Okay? So that's conduction. So conduction works only in solids and it doesn't work over large distances. Okay? So what I mean by that is if I'm looking at, let's say, a section of exposed earth in Mexico. Okay? Sun is shining on that part of Mexico, okay, and that part of the ground is absorbing energy. That energy is not going to be transferred to Canada through the Earth's crust. Okay? It is not going to be conducted over thousands of kilometers, okay, through the Earth's crust by particles running into each other. Okay? It just doesn't work that way. Conduction really only works over short distances. Okay? Here's another example. If it's a really cold day and there's something metal, okay? If you put your hand next to but don't touch that metal object, does it feel cold?
Mm-hmm.
If you don't touch it?
Yeah.
It doesn't feel cold until you grab it. Then suddenly it's like, oh, that's cold. Okay? You can't conduct energy to it and lose energy and thus feel cold until you actually make contact with it. Okay? Conduction only occurs if there's physical contact and over very short distances. Okay? Making sense? Okay? On the other side of that, okay, if I had like a big sheet of, let's say, like aluminum, and I put my hand on the bottom of it and it's like, let's say, 3 meters tall, is the top of it going to get warm because I'm touching it?
Eventually.
Realistically? Is it going to get
Eventually.
warm, like 37 degrees like my body?
I mean, if you wait long enough, it'd be perfect physical world.
No, it'll radiate away before it'll conduct that far. Okay? We're not talking about this being able to transfer energy over great distances. And by great distances, I mean not even a few meters does conduction generally work very well unless there's just a massive amount of energy available. Okay? So conduction is not a global energy transfer mechanism. Okay? Because it just doesn't transfer over large distances and only through solid materials anyway. Now, this one is convection. This one is probably the most important. Convection is heat transfer in fluids. Gases are also fluids, by the way. Okay? So convection is hot air rises, cool air descends. That's a convection curve. Okay? When that happens, when air can flow like that, okay, you can transfer energy from, let's say, a radiant heater. Okay? So in our houses, okay, most of us probably have a forced air furnace. Okay? And so we have vents in the floor, okay, that blow the hot air. Agreed? Why are the vents in the floor? Because hot air goes up. Now, if in the basement, they're in the roof simply because it's hard to run them through the concrete foundation of your house. Okay? But on all the other floors, your main floor and maybe your second story, okay, the vents are in the floor. Okay? And that is because they're blowing hot air and the coldest air is going to be nearest to the floor. We want the hot air to encounter that. Hot air will rise, cool air will descend. Okay? So in the summertime, if you don't have air conditioning, where do you hide? In the basement, because cool air descends. And if you don't have air conditioning, the basement is the place for you because the top floor is probably going to be 28 degrees. All right? Making some sense? Okay? It's also what works in here. Okay? I use a little bit of radiant energy and a little bit of convection in here to heat this room, because I actually turned up the heat the other day and it didn't seem to make a lick of difference. Okay? I still use you guys to heat this room. Okay? You're hotter than the room. Okay? Radiant energy flows out from you into the room. Okay? Hot air will rise. It's a little warmer at the ceiling than it is at the floor. Okay? Making sense? Now, in North American houses, does air conditioning work very efficiently?
Why wouldn't it?
Well, because we use the same vents to air condition our houses as we do to heat them, which means we're putting cold air from the floor.
It makes the floor nice and cool.
It makes the floor nice and cold. You walk around barefoot, and you're like, oh, that's so nice. Okay? But typically, like I know I have to do this with my furnace, what I do is in the wintertime, I don't run the fan, I don't turn the fan up as high. Okay? You can actually adjust that. Okay? I don't run the fan as high because I don't need to. Okay? The hot air will move upwards on its own, but in the summertime, when I want to blow cold air, I turn the fan up all the way. Okay? So it forces the air out of those vents and upwards. Okay, causing that cooling action to happen. But in the summertime, I have to work against the way convection naturally wants to work. Okay, everybody all right with that? Okay, so convection, okay, is the main source or the main method by which energy is transferred on a global scale. Okay, hot air rises, cool air moves in to replace it, and that happens on a global scale. At the equator, where most of the solar energy is coming in, air gets hot, it goes up. Air moves in from the north to replace it, okay? And that hot air moves north, taking with that moisture from the water cycle that we talked about, okay? As well as the sensible heat that it's absorbed by just getting warmer, okay? And that moves to the poles naturally by convection. And we feel that as wind. Okay? Wind is evidence of convection occurring, okay? And moving energy around. All right, and then the last form of energy transfer is radiation. Okay? That's how energy gets here from the sun. It's also what you feel if you're next to a campfire. Okay? So if you start a campfire and you're like warming your hands on it, you're not using convection there. Okay? You're using radiant energy. You can feel the energy coming in waves. Sometimes you can even see, right, the distortions in the air that those waves cause. Okay, as they're moving towards you, you're using radiation to heat you. Not the kind that will turn you into the Hulk, okay, but the kind that will make you warmer. Okay, because we all know the Hulk was created through gamma rays, okay, not through infrared. Right? So it's going to be that infrared radiation that's coming off. That's what you feel. Okay.
So the closer you are to the sun, the more likely you are to be the Hulk.
Yep. Or fried.
Or
Probably fried.
But there's a possibility.
Sure.
I think it's worth a try.
Worth a try.
That's the one.
You get a great tan.
Only live
Worth the
once.
risk.
Yes, there's a whole other,
Yeah, what's their award?
being, exploding.
Put some sunscreen.
We'll just send Jackson. up
Yeah,
there.
1 million sunblock is available somewhere.
Jackson will either become the Hulk.
Yeah,
or-
I'll either
Or
become
he'll become the crisp.
I'll either become the Hulk or I'll have some gnarly skin cancer.
Yeah. Okay, so here's how this is going to work, guys, in terms of like an application type of question on an exam for you. Okay, I might ask you again to explain how something works. Like, let's say, go back to the Quincy, where I might ask you design a building or a structure that could keep food cold on a hot sunny day. Okay, so if you wanted to keep food cold on a hot sunny day, and you were building a structure to do that, what color would you make it?
White.
Why?
Because white
Because of
doesn't
the way
absorb
that it
heat.
is.
White doesn't absorb heat, right? It has a high albedo and would absorb very little radiation. So you tell me, there's the first method of heat transfer and how I would thwart it. Okay? Then I would probably have something that would either circulate air on purpose to keep it cool, or something that would maybe prevent circulation of air, okay, so that heat couldn't be transferred in. Okay? What do we use in our homes to prevent energy being transferred from the inside of the house to the outside?
Insulation.
Right? Why does that work?
Because it's big stuff.
Because it's pink stuff.
Because of the way that it
It
is.
looks like
Because of the way that it is. All good answers, but not very specific. I'm giving you like 1 or 2 out of 5 on those. Okay, here's how insulation works. Okay, so here's my wall. Okay,
Pockets.
this is inside the wall. This is outside. Okay, so it's cold outside. Now, I put the pink stuff, okay, which is made of what?
Cotton candy.
Fiberglass. Looks like cotton candy. It's fiberglass. So these glass fibers are incredibly small. You never want to handle fiberglass insulation without proper gloves or a mask on, because you can actually inhale the glass fibers.
And glasses.
Okay? Yeah, it's bad. So what fiberglass is tiny little glass fibers that kind of interlock, okay, and gnarl around each other. But in between all of these glass fibers is what?
Air.
Air. Can that air move?
No.
No. It's trapped.
So it's
By trapping the air, you prevent convection from occurring. If convection is going to occur, hot air has to be able to go up and cold air has to be able to go down. That can't happen in an insulated wall. Okay, because there's no way for a convection current to form. If I just had a wall that was empty, okay, this side's hot and this side is cold, okay, here's what happens. The air closest to the hot wall goes up, okay, the air by the cold wall moves over to replace it, and I get a convection current going on inside the wall that happily transfers all my energy from inside my house to outside my house.
Could you just fill it with sand?
Sand would allow conduction to occur.
Could you fill it with clay?
Okay, the benefit, well, that's still a solid. The benefit of the fiberglass is that glass conducts energy very poorly. It is a very poor conductor of heat. Okay, but secondly, it is unlikely that a glass fiber that makes contact with this wall is actually in contact with that wall. Okay, they're gnarled all over the place. I've drawn them like hashed lines, but they really kind of just go everywhere. Okay, and they create these areas of trapped air. Conduction also can't occur through the air. Conduction only occurs through solids. Okay, so by trapping all this air, you not only prevent convection, you also prevent conduction. The only parts of the wall that are really going to transfer a lot of energy through are the studs. That's the wooden parts of the wall, because they're actually in contact with the outside and the inside, and some conduction can occur. Wood is also a poor conductor of heat, so it's good that we build our houses out of that.
So would this is what happened, like when Texas got snow, and it was like -1, and they were all freaking out because their houses weren't insulated?
Weren't insulated, most of them don't have furnaces.
No.
Yeah, they never have to worry about that, right? So yeah, most of them don't have some way to heat. In Canada, especially in places like Newfoundland, they have like 3 different ways to heat the house, right? If the power goes out, well, they got, a generator that can run an electric, electric heater, and when the generator runs out of fuel, they have a wood-fired stove, right, that they can heat the house with. Right? We're concerned with that. In the summertime, less of us have air conditioning, but yeah. So when they got that cold snap in Texas, that was exactly what happened.
And their pipes.
Almost, there was no need for a lot of insulation, but they still insulate their houses for heat coming in. But mostly that none of them had any way to heat their home. Okay, so does that idea make sense? That's how insulation works, okay? Styrofoam is very similar. Okay, if you have styrofoam is a bunch of little pockets of air trapped within the foam itself. Okay, so foam insulation works very similar. What about like, if you have like a Yeti or a thermos, how do those mugs work? What do they have inside?
There's air in between.
Not air,
Something else in between.
something else, or the absence of anything. A vacuum. So, the way you typically design one of those thermoses is you have the inner vessel that contains the liquid, okay? And then what you do is you have basically a vacuum chamber surrounding that, okay? If there's nothing in there, conduction can't occur. Conduction can only occur when molecules are packed closely together, okay? And you also can't have convection occur because there's nothing to move, okay? And generally we make the inside shiny, which would cause the radiant energy from the liquid to reflect back. Okay? So all ways that we harness, okay, are our knowledge of heat transfer to do useful work for ourselves. Okay? All right. We talked about the water cycle already. Okay, the hydrologic transfers of energy. So when the water evaporates, that's an input of energy. Okay, there's all this latent heat that gets carried. We're going to talk more about latent heat later on in the unit. Okay, to other areas. When it condenses, it's going to release that energy as sensible heat and mechanical energy. Okay, in the running water. Okay, and then for the lithosphere, okay, basically it's just the albedo part. Okay, the lithosphere absorbs energy, okay, because of its color. Okay, so write these ones down, guys, the 3 fates of solar energy. Okay, I'll give you a minute to get those 2 written down, and then the last one, and then we'll call it good for the day there. Okay, we did talk about all 3 of those on the very first slide, but there wasn't any mention of them in the notes, so you just need to add those in. Okay, reflection, absorption, and conversion.